with emphasis in artificial intelligence and computer vision from Chunbuk National University in South Korea. Mechatronics engineering from the Technical University of the North, Ecuador. He did his bachelor's from Ecuador. He is currently a postdoctoral researcher affiliated with the Core Research Institute of Intelligent Robot of Jeonbuk National University. He is the research group leader of Multimedia Laboratory of the Jeonbuk National University. Throughout his career, he has also participated in several studies and research stays in Germany. He has authored and co-authored several publications in indexed journals with high academic impact. His current research interest includes machine learning, deep learning, and computer vision with various applications in robotics, smart agriculture, healthcare, etc. So I'm very happy to welcome Dr. Alvaro Fuentes. And now you can start delivering your talk, Dr. Alvaro. Yeah.
Okay. Can you see my screen?
Yes, we can.
Okay. Yeah, great. Good afternoon. Thank you very much, Dr. Sunil, for the kind introduction. I'm very glad to talk to you today. So best regards from South Korea, where I'm currently right now. So I have prepared a talk about the contents that I've been working throughout the recent years, since the 2014-15, more or less. Those are closely related to topics of deep learning and IoT for smart agriculture. And I'll cover some of the contents basically related to AI and our main work on plant disease recognition. And I divide into different topics based on the contents and works that we have developed instead of model-driven, data-driven, environment-driven, and our most recent works on high throughput monitoring for the area of plant disease recognition using various types of sensors and mainly cameras, but also other type of sensors in greenhouse type of crops. So I'll start as mentioning, as we all know, and we are very familiar with the topic of AI nowadays. So today I would say artificial intelligence is a very thriving field with many applications, and it's a very active research topic. And it all starts with the development of industrial revolution. So we start by the first one, and we went to the second and third, and now we talk about the fourth industrial revolution, where the information technology through the big data and IoT and cloud computing systems, along with internet and artificial intelligence software and developments in this area. So both together make something that is more advanced and can be applicable for several parts of the industry and in research as well. So conceptually, so deep learning comes from the concept of intelligence. So we all know that intelligence could be say that this is the ability to process information to inform future decisions, or based on the information that we learn, probably predict something in the future. So we got a big area, and that's called the artificial intelligence. It could be regarded as any technique that enables computer to somehow mimic human behavior. And then we got to other areas of artificial intelligence. One is the machine learning. So it's the ability to learn without explicitly being programmed to perform a task. So we got big data, and we got an algorithm, and we apply that algorithm to somehow understand what is behind that data. And then deep learning goes a bit more further, and we say that we can learn automatically those patterns extracted from the data using neural networks. So, and deep models have been proposed throughout the years, especially I would say in the last decade. Several advances in the area have been proposed, mainly through challenges. But nowadays it's a thriving technology that has been applied to several fields of research. And so neural networks are not new, so they date back decades, but recently became so popular And we heard that three main reasons contribute to that development. We start with big data, so we get big, large amounts of data available, and data sets which are easily accessible for research purposes, and not only in terms of images, but also in other type of data sets like audios and videos and various type of, it depends on the application. We also have high computing power systems like GPUs and that allow training processes, speed up those development processes, and especially training and development of the AI models. And we also have another field of very important high breakthrough is the software. So we got new techniques, new models, and new toolboxes available also for development. So we got very famous toolboxes that are applied in AI field and easily accessible and open access for development. So those three breakthroughs contribute to the development of AI during the, I would say, the last decade, as I mentioned, and it became so popular and is now accessible for everyone, and we can apply it to various fields. So in terms of talking in terms of innovation and the areas that has been developed during the recent years, and I will focus on agriculture. So agriculture became so popular, I would say, in around 2017, 18, with the concept of smart agriculture. This is a graph from the World Forum. And now we've seen a lot of developments, and in the current state that we are now, so we are seeing some of the developments more emphasized on the autonomous farming. So the use of technology, mainly based on AI and robotics together to make systems more autonomous and more efficient in the field, and basically to increase the yields and make processes more efficient. So we've seen a lot of developments during the very short period, but our research is mainly focused on very big field about agriculture. And this starts, I'll say, this model that was a model proposed by the United Nations called AI for Good. And it covers 17 different sustainable development goals. So we are mainly covering one, is in the area of agriculture, is a way how to use artificial intelligence or technology to increase the agricultural productivity and somehow do not cause any impact on other fields. So we are trying to basically optimize processes to make it more efficient. So given that background, so I'll give some important facts about South Korea and why we start with this project by the year 2015, more or less. So Korea is a small country, but the population is about 51, 52 million by the 2020. In terms of land use, as this is a highly populated or densely populated country, we'll say that only 16.7% is an agricultural land. It's mainly covered by forests and cities as well. And there, as a small country with no agricultural land, so it's difficult to cover the necessities of the people. And another issue is the rural population is being reduced. So people tend to move to the bigger cities, mainly like Seoul or surrounding area. And so there is not people who want to dedicate to the agricultural area, or people who don't want to become farmers. And so there's a lack of people in that area. So, and the other one is the land cover. As I said, there is no area to cultivate. So the only solution, I would say, for producing goods in Korea is through the use of greenhouses. So sometimes we may see greenhouses for strawberries, for paprika, for tomato, for some of the crops that could be adapted to the weather in this part of the world. And so we realized about those issues, and we thought about something related to smart farming. So using technology media, using available AI technology, sensors, and to develop some advanced systems that could somehow help to overcome those limitations. So, and we found this big area, which is called the plant diseases and pest recognition. And so mainly the idea was to design a product or a system that could probably detect diseases at that time. And of course, the diseases are closely related to the high quality of the products and also the cost as well. So we wanted to develop a smart farming method that could somehow help to solve those limitations in the area of agriculture here in South Korea. So we start by analyzing the plants and how the plants are affected by any pathogen. So we will see that once a plant is affected by any symptoms, diseases, physiological disorders, and viruses. And so once the plant is affected, so it could be easily propagated to the entire crop. And as a result, we might find a lot of problems in case that losses, economical losses, and productivity losses. But those are not only the issues that cause diseases. We might see issues closely related to environment control, diseases, pests. A lot of variables are involved into this. So a plant is a very complex unit to be understood. Starts by a seed and it becomes a plant mature, flowering, and then we get products. But traditionally, the idea of crop protection issues start with farmers. So usually, traditionally, I would say the farmers go to the field, observe the indicators, if the plant is in good condition or not. There's a daily routine, it's a close examination, and then combining those indicators, so we can make an assessment. So what will be the issues that are present now, and what could be the farmer do in terms of improve those issues and generate a better state for the plant. So there are several questions in this regard. For example, I'll say, is the growing process functioning well, if the plants are behaving well, or the expected yield is somehow obtained, and a lot of questions in between that traditionally are done and executed by people going through the field and checking the processes, which somehow demands a high expertise in the field and to understand these complex systems. So also, considering that traditionally diseases are treated by chemical compounds, so basically once the farmer detects a disease, so there is a lot of chemicals spread to the crop, which of course are related to the is harmful for the environment, human health, and plants as well. And the other issues I have just mentioned, the agricultural labor costs are increasing because there is a decrease in the agricultural population. I'm talking about Korea. And also the diseases, of course, that cause several economic and production losses. So those three points were important for us at that time. And we decided to work in some challenges so closely related to plant disease recognition in real field scenarios. So scenarios that are various types of greenhouses. So you can see some of more advanced ones with more technology, more sensors implemented, some actuators as well, and some traditional ones, which are the local ones managed by farmers, local farmers that do not have all the advanced control system that those with more technology. So in real field scenarios, we find a lot of variations. We have a lot of diseases that change from greenhouse to another greenhouse. It's difficult to collect data because those are seasonal products and demands an expertise to detect the diseases and collect data. So since our work was related to images, so we need to capture images in the field, go to the farm, along with a domain expert that indicates this is the disease, these are the symptoms, and those are the infection stages, and those are the levels of occurrences. So a lot of unknown information as well, some new diseases, new type of symptoms that a plant can show depending on the conditions that it applies. So, and also there is something that's called domain shift that changes the environment from farm to farm. So a system that is developed in one farm can only possibly be applied to another farm because of those changes in the domain. So we got a lot of problems in that regard. And we start by analyzing some path or roadmap for our implementation. So we start by something that's called model driven. So we got
Dr. Alvaro.
Yeah.
Yep. Dr. Alvaro, yeah, can you turn off your video, because sometimes it is like there is an interference in the voice.
Yeah. Okay. Yeah. Okay. Yes. Now.
Yeah, thank you.
Yeah. So we start with something that's we call it model driven. It's a core technology. So we develop the core technology for plant disease recognition and deep learning. We collect the data set and we develop that technology. So continue with that. We are another stage that is called data driven. So basically trying to improve the models that we have developed and use more advanced techniques. For example, data augmentation proposes on some data optimization and enhancement. So in order to improve the performance of those methods. And then we went through another stage, and that stage was always about developing more adaptive models that could be generalized for any type of greenhouses and that could be applicable in different environments, not only here, but also in other medias as well. And as another advanced stage, I would say we work on high throughput technology, and this is the use of more advanced monitoring systems, crop growth model estimation, and use of other type of sensors like IoT sensors, including, for example, temperature, humidity, light conditions in the greenhouses, and also the applications of robots that perform those tasks. So that's the roadmap that we've been following throughout the years. And according to that, I have prepared some of the works that we have proposed for that. So starting by the model-driven approaches. So we start our system, developing our systems with a data set. The data set was not available, so we needed to collect our own data set. And we focus on tomato plants. So we developed somehow a strategy to collect data, going to the field and collecting images with various resolutions, samples at different infection stages, different infected areas of the plant, different sizes, and different types of greenhouses. So to capture all those variations required to teach a model. So then we realized about the idea that it's important to detect not only the presence of one disease, but probably somehow we need to detect the presence of multiple diseases. So we start by analyzing the data and trying to find the proper strategies, and we came up with the idea of using object detection. That's an area of computer vision that aims to detect objects in the images. We apply to the plant diseases area and came to this concept that we detect not only what, but also where through the bounding blocks in the image, so we can certainly know the location of the image of the disease, the symptoms that are happening in the image for later proposals that now we've been applying. We tend to apply robots to perform the task. So we collect the data set, we got positive samples, negative samples. Let's say we got positive in terms of the types of diseases, different multiple diseases in the same image. And not only diseases, but also viruses and pests and insects with different scales, different infection status, different greenhouses. And the system is mainly divided into these diagrams. So we'll say we got an input image and we got a deep learning model, and there is a feature extractor that basically collects the features from the image, and we got a specialized detector that provides the probability, the class probability, and location through the bounding box in the image. This is general overview of the system. And then we went through the design and implementation. So we start by collecting the data set. We annotate the data set by using bounding boxes. So once the data set is annotated, we apply some data augmentation techniques to increase the number of images, for example, geometric transformations, intensity-based transformations. And so once we got our annotated and augmented data, so basically train the model and validate the model on the available images. And we verify the performance of the model and obtain the final results. So that was our initial model back in the year 2016 or 17. where the model was deployed in the farms and it was tested by the farmers here, and we somehow got a good acceptance in the community, and we obtained at that time a performance of 83% in average for all type of diseases, considering that some of them are more complex to detect and more relevant for the farmers here in this area of in Korea. But later, in order to improve those works, we found that some of the diseases present some features that are very complex to handle, and they have some similarities with other diseases. So we came up with another idea, and this is to solve the two main problems. The first problem is the class imbalance problem. So we got diseases, of course, and every disease have different symptoms and are difficult to collect. So some of them are more frequent, some of them are not. So the most frequent ones are easier to collect. We got more data, more images, but the infrequent ones were difficult to collect and the number of images was very reduced. So that's a very big issue in deep learning models. So class imbalance problem. And we got another issue. Those are the false positives caused because of the class imbalance. So in our first model, we found that about 10% of the samples were false positive detected. So it means they do not belong to the same class that it was expected to have. So those two big issues were solved with our second version of the model. So STARS is divided into several units. We start by a first unit, which is mainly the detector that we apply in the first stage to obtain the bounding boxes and sizes and different detected regions. And then we got another secondary diagnosis unit. So that diagnosis unit is mainly in charge like a judge function to determine whether one object was correctly detected or not. And if not, so the system will basically generate a signal that is true or false. And if that is true, it will be correctly detected. And if that is false, it will be reassigned to the corresponding class. So in the end, we have some more improved method. And this method obtained 96% in average, which is a 13% improvement over the previous method. So, and we were able to detect 10 types of diseases, pests, and viruses, including very tiny insects and other diseases with large influence and others with minor influences, but somehow important to be detected. So we obtained this performance. And then we're trying to overcome the limitations of the current situation. So we proposed a model. So we start by classification. Then we went through classification, localization to obtain the bounding boxes. And then we decided to make a model more advanced using captioning to somehow provide a sentence as output along with the location and bounding boxes. So that was easy for the users and to understand the situation, the symptoms of the plant and related to several characteristics. So we designed that architecture following some specific descriptions that mainly describe the symptoms of the plant. And every section of the image, and then we went through another abstract description that describes the scene of the plant. So that gives a general estimation. So we generate some language. So in terms of here using types of diseases, location in the plant, symptoms, some colors, infection status, and those are all interconnected to somehow generate a language that describes the global and local attributes and including background information of the image. So we make those system and we train the model, including a vision and language generation to describe the specific symptoms and also the abstract description of the scene. So what we obtain is a model about 92% in average. And that model, of course, was able to detect and describe the symptoms and also locally and globally the scene of the of the disease or the status of the plant. So that was easier initially in English, but it could be also translated to other languages. So that's what we thought at that time. So in considering those works, we went through another stage, and that's the stage of data-driven approaches, where we try to improve the previous developed models using more advanced techniques to mainly work on the data imbalance problem. So we realize, again, continue with the same topic that we had before, I mentioned before. We got data sets that are easier to collect and others that are not frequent ones. So our idea is to somehow use images or image-based techniques to increase the number of images artificially. So, and that's the idea of something that's conceptually is called image-to-image translation. So we put features from one disease image to the healthy leaf, and the other vice versa, the other direction as well. So we can generate healthy leaves based on the disease ones. And so this work was proposed by the year 2020 using generative adversarial networks to do that. So we were able to control the diseases and put some disease symptoms on healthy regions of the leaves. So these are some examples with different diseases and even insects that were put into the same area. So we can have from one healthy leaf, we can have a lot of disease images, images of disease leaves. But thinking about more as a more advanced problem, so this type of data we applied for object detection as well, and the responses are not as well as we expected in 2020, I would say. So because of the region are complex to handle, and those are ROI regions that do not cover many complexity of the background. So what we did here is recently we proposed a new method. So in this method, through this method, we can control different degrees of infection and also a more advanced estimation of features of the images. Again, using a generative adversarial network and the concept of image-to-image translation. So we somehow generate new data with higher quality features. So, and that was the key issue, was applying instance segmentation to translate some regions of the leaves in the big image, so including complex background conditions. So we applied this generated data, and this data for various tasks, where you can see here for object detection, instance segmentation, or classification purposes. So we got an improved classification accuracy in terms of using only traditional data augmentation techniques. So these images were clearly enough to be detected, and these are some examples of the detected results using those artificial images that sometimes is even hard for the human experts to identify if that is an artificial image or it is a natural image. So we applied those techniques and we got better results. And then we went through another topics, which are the environment-driven approaches. So we basically, what we think about here is that the domain shift problems. So we got farms with different conditions, as I mentioned earlier in the presentation, some more advanced ones, some more rust and traditional ones. So different changes in terms of infrastructure, environment, background lighting, and also different types of diseases. So in deep learning, it's very well known that once we develop a model in data from one specific farm, for example, and we want to deploy that model in another farm, somehow it could not perform as good as we expect because of those variations in the domain. So the idea is to understand the complexity of the data, and considering that in real field scenarios, we might find some known diseases, which are very easy to detect by people who are involved into the agricultural field, but some unknown data that somehow are unknown to the system. So the model was trained with known data supervisedly, but in real field, we might find or frequently see unknown data that limits the performance of the model, as those type of images will be assigned to one of the known classes as response. So our idea was somehow using a concept of self and a cross-domain adaptation. So we took features from one farm and put them into the second farm and train the model again. So it comes from the concept of transfer learning, but in this case we mainly use for domain adaptation. And the key points in this work was recognizing not only known diseases, but also recognizing unknown information, unknown diseases that are known to the system that could be present in the new farms. In that sense, we can closely relate it to the information that is unknown and find a solution for that, whether there is a new type of disease, a new type of symptom that the model didn't learn. So, and the farmer could be able to identify it. So this type of idea is more applicable for real field environments as a more general system that could perform more complex estimation. So our idea starts by transferring features from one farm to another farm, which are the domains. We got known classes and we got unknown information, and this is captured from farm to farm. So we call it a cross farms domain adaptation. So from one farm, we call it up to the other farm, also in the same farm as well. That's called self farm domain adaptation. So the system conceptually starts by a detector. The detector provides refined bounding boxes and classes, so detecting the regions that contain the disease. So, and then we got another module that's domain adaptation. So basically to adapt the domain from one farm to the other farm. And that system was able to detect the known and unknown classes. So the model of domain adaptation works in a way that we use data from a source farms, including known classes and also some background information to give more context about the farm. We train a model, we extract the features. So once we obtain the features from that source farm, we transfer the features to the other farm. That's the target farm. And then we are able to use unlabeled data, so that using that unlabeled data, in the end, we train the model again using the features obtained before, and the model is able to understand again what is known classes or unknown classes. And so, and our result was surprisingly effective, and we were able to estimate unknown data in the farm. So when disease is not present in the model initially trained, so it will be detected as unknown. So this model could be applicable, as I said, from farm to farm, and it's more advanced technique that solve the problem of domain shift. And so this model is being developed for tomato crop, but we are extending our research area to other types of crops as well, such as strawberries, paprikas, melon, and in Korea. So since I already mentioned the model-driven techniques, data-driven techniques, and environment, I'm going now to the more high-throughput crop monitoring, where we like to understand the entire cultivation process of the plant. So basically using monitoring cameras to understand the features of the plant that show different levels of development, starting from the small plant until the fully developed plant and production stage until the plant is not anymore productive. So we got a lot of variations, a lot of variables that we need to monitor during the entire cultivation period. And there are some counts in between, for example, some information that could be obtained for the plant, and that is regarded to the conditions. For example, counting the number of leaves, measuring the stem diameter, number of flowers, fruit, and some additional variables. Also, understanding some monitoring levels in terms of stress, nutritional efficiency, or those symptoms that a plant shows throughout that period. So this is our current technique, and we are trying to understand the plants, as I said, throughout the entire cultivation period. So our data is, our systems are being deployed to these real field scenarios, starting by small plants until the big plants as they grew up. We obtained the variables, and the deep learning models are deployed here to understand the entire cultivation period. And this is something that's called the plant growth estimation. So we use multi-category data, starting by our greenhouse experimental site. We got some environmental data, for example, light, temperature, humidity, and CO2. And then we also obtain data from the root zones, especially the batches, since this is a hydroponic-based system. We measure temperature, humidity, moisture, EC. And we also obtain image data. So from that image data, we basically obtain the phenotypic information related to the leaves, flowers, and fruits. And along all of those three types of data together, we call it multi-category data as an integrated spatial-temporal data that follows the entire cultivation process. And we've been using those processes, and now our current implementations include the use of robots to perform the detection task, and also the deployment of the models in the demonstrative or experimental sites that we have. So the objectives in general through our developed technology is this is a part of a strategy of the Korean government that became or developed by the Korean government recently. So we start by indoor sensors using camera devices and environmental sensors and nutrients control. We have cameras. We got also outdoor sensors out from the greenhouse, so finding the corresponding information or relation between indoors and outdoors. We got also robot controls that perform the task of monitoring the crops. So once we obtain all that information, we can certainly generate a model that helps the farmers to understand the conditions of their crop. And this works all through the cloud services, so the people in the field can use those type of systems to that do not demand the expertise, but the use of this type of media to solve the problem that they have, not only related to plant diseases, but also to crop in general understanding. Yeah, so as a conclusion for my presentation to finish there, I would say that our decisions were fundamentally task and cost specific. So we developed the models, we deploy the models, and they are implemented, and they demand different needs, depends from country to country and the available resources. The availability of data is still a challenge, so it's difficult to obtain data. And of course, creating a general pulse system is still difficult and still a difficult challenge that we've been working on, how to develop a general model that will be applied to different environments. And our techniques certainly help the farmers to estimate the plant diseases and avoid economical losses. And we have proved that here, and people that utilize our technology. And last but not least, I would say generally a responsible use of AI technology is a key aspect to achieve a sustainable development, not only in the area of agriculture, but also in any field where this technology plays a key role. That's all for my presentation. Thank you very much for your attention. If you have any questions, I'll be happy to hear from you. So if not, this is also my email and website. You can easily reach me out. And I'm always happy to get comments. Thank you.
Just unmute him. Thank you, Dr. Alvaro, for your nice presentation. It was indeed an interesting talk, especially for me, because I'm also looking this smart agriculture thing for at least curiosity thing, this aquaponics and all this thing, but not in terms of research wise. But I have a curiosity. I will ask my question in the end, but let me check if I have question from the participants.
Yeah.
Participants, if you have any question, you can ask. I will unmute you. Okay. So, Dr. Alvaro, I have a question. I mean, these images which you are taking and doing this processing for disease detection, you are using drone, or how it is collected?
Not exactly drones, because we had greenhouse type of crops. So while using drones is difficult in the greenhouses. So I'll show you one image. But the greenhouses, as I said, so these are the greenhouses.
Okay.
So once the plant grow, and those are big plants, so they will reach about 10 meters. So there's a huge overlap between plants, and it's difficult for a drone to move into those spaces. So that's why we didn't use drones, but we took manually images by phone cameras, by other digital cameras. So people went to the field, take images. Also, we got images from the farmers that collect, for example, they were curious about what is that disease. So we obtained those images from research centers as well. So to make our database. And then to deploy the models, so we deploy with the smartphones through the develop application. So the people use that app. And now we are implementing with robots. So the robots, robot arms or other types of robots will basically be in charge of monitoring the crops and detecting the diseases and saving that information for monitoring purposes.
Okay, so basically, if we are going for the smart agriculture, that too in open field, we can think of integration of this drone source with this technology.
Yep. Yeah, definitely. If you work in outdoors type of crops, of course, we can use the drones or any other media as well. Yes.
Okay, I have one more question regarding this disease diagnosis that to at the root level. So I have a question. I mean, can we include technologies like this or this? You might have heard this model communication. This communication using transmission of chemicals or molecules. So if we are using this aquaphonics techniques, in that, especially in that case, if we deploy some sensors and the disease which are root borne, we can take track of that disease. So can we integrate this model communication also for this smart agriculture?
Yes, definitely we can. And if you look at this image, we got those batches, and those are where the plants are basically cultivated. And if you see here in this area where I'm pointing out, so there is a weight. So we measure the weight of the batch. So based on that, also the sensors are located in the root zone. So we measure those variables that I said here, temperature, moisture, easy. And of course, the communication goes in a way how to interconnect those sensors and the information coming from different sources and to make the proper decision. So it's a properly integrated system. Yeah.
Right. Okay. Thank you very much. So participants, last time, if you have any question, you can ask. Okay. So just for curiosity, I have one more question, Dr. Olivero. I mean, this whatever the research you have presented, is it like you are collecting data from somewhere else and then doing this processing, or you are doing this research from end to end, the whole thing?
Our research has been developed entirely from us. So the data is our data. Let me show you. Yeah, so the data is our data. So it's our own data. So we collect the data. So the current data set is about 20,000 images, but it's been increasing every year. Every year we've been constantly updating our data set, not only in tomatoes, but also we got other data sets. So unfortunately, we couldn't make those data sets open access because those are part of projects here in Korea. And there is a limitation not to open the data sets until the projects are concluded. That's why we keep the data set by ourselves and develop the models on our own data set. So this data set has been updated. And so now we've been collecting not only images, but also other type of data sets, including, as I said, environmental data with the sensors and communicated in the greenhouse. and also nutrition. So the root sensors that provide information of the status of the plant. And of course, the purpose is to develop more advanced techniques, more understanding of the crops and cultivation, and possibly develop new sensors and new type of methods to solve those problems.
Okay, okay, sir. So here I have, sir, a last question from the participant. Is the accuracy of the model decreases if we take data from different crops to predict the disease? And if it is the case, then how that can be improved?
If you design a model for a certain disease, I would recommend you to use independent datasets. So if you develop a model for tomato, that model could not probably work for corn or for bananas, or because every plant has different features. So we need different datasets for those purposes. And also depends from disease to disease, of course. And there are currently some available datasets online. One is they call the plant VH dataset that was proposed similar time that our work. But their work is really mainly on classification, and the complexity of the dataset doesn't include, for example, situations of the real greenhouse. So once you use that dataset that has some, so to collect that dataset, they crop the leaves, they cut the leaves, and they took to the lab and put them on the table and take the pictures from the top of the top view. So the background you might see is a table background with a leaf on the. So the complexity is somehow not the one that when you deploy the model. So let's say you teach the model with those type of images, and then you try to predict the diseases in the real farm scenarios where you can find those circumstances or those variations that I'm showing here in the pictures. The system tends to fail. So you need to collect the proper data set with the proper variations and teach the model with those images, and then you will get probably better performance. But there are various complexities in the development process as well.
Okay. So thank you, Dr. Alvaro. It was indeed a nice presentation. I think that our participants will get benefited from this, especially because we talked about these days a smart thing using this IoT. So yeah, thank you, Dr. Alvaro, for accepting our invitation and for this wonderful talk. Thank you.
Thank you so much, and I wish you have a good event. And I'm always able to for any communication questions in this regard. So this is my email and my website, so you can easily contact me. And thank you so much for the invitation again. Yeah.
Okay. Okay. Thank you, Dr. Alvaro.
Thank you.
Participants, we'll have the next session at 3:30. So please do join that session. It will be talked by Dr. Umesh Sampath, and the topic of presentation will be recent advancement in fiber optic communications. Good afternoon, Dr. Umesh Sampath. Can you hear us?
Hi, good afternoon. Yeah, I can hear you.
Yeah. So, Dr. Sampath, we'll wait till 3:30, then we'll start.
Yeah, definitely.
Okay.
Yeah. Okay.
Yeah. Okay. Thank you. Dr. Sampath, can you hear us?
Yeah, I can hear you.
Yeah. So shall we start?
Yeah, definitely. Yeah.
Okay. So very good afternoon, Dr. Sampath. Yeah. So Dr. Umesh Sampath received the B degree in Electronics and Communication Engineering from Anna University, India in 2012, and MS and PhD degree in Electronic and Information Engineering from Chonbuk National University, South Korea in 2016 and 2019 respectively. His research interests are optical fiber sensors and optical engineering. Currently, he is working as a senior research engineer, Electronics and Control Engineering R&D Group, INZI Controls, South Korea. He is currently working on the sensor and control design for the next generation vehicles. He has published numerous papers in well-reputed journals and conferences. So today in this session, Dr. Sampath will give a talk on recent advancement in fiber optic communications. So over to you, Dr. Sampath. You can start.
Okay, thank you. Thank you for your introduction. And also I like to thank SRM AP for conducting this wonderful program. So I will proceed with my presentation. So I will share my screen.
Yeah, please.
Could you see my screen like it is visible?
Yeah, we can see.
Yeah, okay. Good evening all. Oh, it's good afternoon, right? Oh, okay, good afternoon all. Like I'm Dr. Umesh Sampath. Today I'd like to give a presentation on fiber optic sensors. So like in optical communication, like fiber optic sensor is also a part, but most of the people, like when it comes to the optical communication, they think about the communication like 5G or bandwidth, those type of ideas. So I wanted to take in a different direction, like, so that's why I wanted to give a talk on fiber optic sensor. So I will proceed with my presentation. The contents of this presentation is categorized into 4 sections. At first, I will give the brief introduction on sensors. In the next part, I will explain about the fiber optic sensor, especially the fiber Bragg rating. And in later sections, I will give some advanced application of fiber Bragg rating sensor, that is on cure monitoring, like composite material, and also the temperature monitoring. Like I will talk about these things in later, and later I will conclude. In general, as you know, like sensor plays a vital part in our day-to-day life. And in recent years, like you can see in every field, like the sensor, it's increasing the demand. And also the environment which the sensor is applied, it is getting more extreme. So there is a need for development in the sensor field. So this is a basic definition of sensor, the device that responds to a physical stimulus such as heat, light. It is a general way of explaining what sensor is. So these are some traditional sensor what we see in our day-to-day life. So next is fiber optic sensor. So I want to explain more on fiber optic sensors rather than the traditional sensor. And what is the need for fiber optic sensor? We have some more traditional sensors which can do the same functions. So what is the need for fiber optic sensor? So I will give a brief explanation. Like the fiber optic sensor is also a sensor which is based on the fiber, optical fibers. It detects the same mechanical things like strain, temperature, concentration of chemical species, acceleration, rotation, pressure, etc. Here, the light interact with the medium and it changes the properties of the light. By observing the property change in the optical sensor, we can analyze our measurement. If you see, like light can be changed in 5 optical properties, that is intensity, phase, polarization, wavelength, and spectral distribution. In this presentation, like I will go in detail on the wavelength related sensors. I will skip the other part, like mostly it will be totally entirely different topic. So I will just concentrate on only one topic today, the wavelength dependent fiber optic sensors. As you can see, like the optical fiber sensor market in the recent years, it is growing drastically. As you can see, the annual growth rate for fiber optic sensor in Asia and Europe market, it's going to exceed like more than $36 billion. So there is more room for fiber optic sensor for advanced applications. As I mentioned earlier, the 5 properties, here you can see the excitation source. So the light passes through a specimen and the receiver detects. So the intensity, either this material can absorb some certain wavelength of light or certain part of light. So there will be intensity change. This is intensity based sensor. And this is also intensity based sensor. And here you can see the polarization based sensor. When the light passes, the unpolarized light, when it passes through a medium, sensing medium, a part of a light is stopped, like only a certain polarized light can pass through the material. So by analyzing the polarization status, we can detect the parameters. So these are the different method of sensing using the fiber optic sensor. Among this, I will concentrate on wavelength-based sensor. This is a fiber Bragg grating. As you can see here, this is inside the fiber optic cable. Like the cable diameter is like almost like 100 micrometer, so which is just like our hair diameter. So there will be a periodic refractive index modulation inside the fiber. So this part is called the sensor, fiber Bragg grating sensor. I can give some, just a moment. You can see my screen like YouTube. Okay. Here you can see the fiber Bragg grating, method of manufacturing fiber Bragg grating. Here UV light is passed through the optical fiber cable. It creates some refractive index change on the fiber at certain point. It is everything done in 10 micrometer range. So when the light wide wavelength pass through this FPG, a part of a light will be reflected back. Rest of the light will be passed. It is like a band rejection filter. So when there is a change in the parameters of this sensor, you can able to measure the temperature as well as strain. So I will explain. This is the method of So here you can see the broadband light. For each sensor, it has a specific wavelength that is called the Bragg wavelength. So if it is past this condition, it will reflect. This is the Bragg wavelength. It is like a band rejection filter in the fiber sensor. If it is not satisfying the Bragg condition, it will pass. This is the condition, and this is the refractive index of the fiber, and this is the grating pitch, the distance between the two refractive index portion. So this is one of the famous sensor in the fiber optic field, which is used for many advanced field like rocket engines. In the later section, I will explain about the applications. Here you can see when there is a strain, there will be a deformation in the sensor. The refractive index also, it will change. So based on this, like we can able to monitor the applied strain. So it can act as a strain sensor. And also when the temperature is applied to the sensor, like the thermal expansion and also the thermo-optic coefficient. The thermo-optic coefficient is nothing but the refractive index change of a material when there is a change in temperature. So it depends on the temperature. The refractive index of a material will change according to the temperature. Based on these categories, like we can able to monitor like temperature change as well as the strain change. So I told like why fiber optic sensor compared to the traditional sensor. Already there are several sensor which is on the field. So what is the need for the fiber optic sensor? These are the reason. If you see the fiber optic sensor, it is very miniature in dimension. It is like 100 micrometer range, and also the minimal mass. And also there are certain field like where you need to monitor multiple parameters. So fiber optic sensor is capable of doing those things, and also the radiation tolerant. As I mentioned earlier, like the applications are getting wider and extreme cases. So there is a need for sensor to work on critical environment. So it should be like immunity towards this type of radiation and corrosion resistance and possibility to work in harsh environment, and also electromagnetic interference. Electromagnetic interference, recent days, like you can see the energy like EV vehicle, electricity vehicle, like hybrid vehicle, plug-in hybrid vehicle, everything it's electric. Like it will work on the battery pack. The voltage will almost like 800 volt, or like the electric field, it is becoming more wider, and the voltage range is also increasing wider. So in this type of harsh environment, like we need to opt a sensor which can work without any disturbance. So that is why we are going for the fiber optic sensor. In this section, I will give the detailed applications of fiber optic sensor, especially FPG. So in recent trends, like the composite material is playing a vital role. As you know, the most of our products, whatever we use, it is made up of composite material, right? From car, aeroplane, everything, it is like composite material, advanced structures like wind turbine, like energy harvesting materials, everything is made up of composite material. It is nothing but fibers and resin together, they make a composite material. So what are the advantages of using the composite material? Like it is high strength, less weight, corrosion resistance, and chemical resistance. And also this type of characteristics, it is advantage. It's a advantage for the manufacturers to produce new infrastructure material. So among this, like I will explain about the wind farm. Here you can see the wind blade, the size of the wind blade, it's keep on increasing, so that the harvesting green energy, it is an important factor. Like people are more concerned about the global warming. So the energy harvesting, here the wind turbine plays a huge role. But there is a drawback. In the wind turbine, like wind blade condition, it is always, it has to be measured. So the health monitoring of the wind blade is very important. So as I told, like blade failures are the major concern in the wind farm, because the increased blade size, the increased probability of failure. If the blade size is small, like you can monitor the blade easily. However, in recent days, like offshore, onshore is onshore wind farm is on the seabed, so you cannot monitor the wind farm continuously. So there is a need for sensor which can monitor 24/7 on health monitoring of the wind turbine blade. In this application, I will tell like how fiber optic sensor is used, especially on wind turbine blade manufacturing. So as I told, like the wind turbine blade is manufactured using the composite material and resin. So we have to monitor the blade. So what we use is the fiber optic. I'll skip this. Okay. So here, this is the material which is used for the blade manufacturing. So epoxy, it cures from the liquid to gel and gel to solid. So we need to monitor the curing process, because the curing process gives the quality of the composite material. So in order to monitor the curing, there is not many sensor which can do that. So we use the fiber optic sensor for monitoring the curing process. So here we use another phenomenon called Fresnel reflection. So when light passes from one medium of refractive index, here you can see the fiber, the refractive index is 1.4. However, the air is refractive index is 1. So when a light passes from one medium of refractive index to the another medium, a part of a light will be reflected back. So it will be reflected. So we can monitor that light and we can understand the properties of the measuring medium. In our case, we use the resin for monitoring. So when the curing is happening, the properties of the material will change. So based on the properties change, you can able to identify the curing process. I'll skip this part. Yeah. So this is the setup. As I mentioned earlier, here we have the FPG. FPG is for monitoring the temperature and as well as strain. Additionally, this part, the Fresnel reflection part, I told like a part of light will be reflected back at the end of the fiber. Using this tip, we can able to measure the resin curing process, and this FPG fiber bragg grating, it is very helpful to monitor the temperature as well as the strain. So this is our sensor setup, and like here you can see this is the wind turbine blade. This is a wind stimulator what we use in we use in our laboratory as a simulator. We use the FPG sensor. Here you can see this sensor. This is a fiber of blade material which we produced in our lab. So we use the fiber bragg grating sensor for monitoring the vibration and also the curing process. Here you can see this from. So this part is for monitoring the curing process. This is while blade manufacturing. So here you can find the reflected light properties. So initially the curing process is ongoing. So once the curing process is completed, the quality, the material characteristics, it will not change. So the refractive index also, it becomes a constant parameters. So by analyzing this constant parameters, like we can able to identify whether the curing process is completed or not. So this is during the manufacturing process. Okay, I'll skip this. Here you can see this is the FPG sensor output. Initially, the resin will be in a liquid state. Okay, so when the curing is happening, the density is increased, and the resin, it becomes the solid state. As I mentioned earlier, the resin, the FPG, it is susceptible to both temperature as well as the strain. So when the resin part is shrinking, it shows more effect on the sensor. Here you can see initially the sensor signal is almost 1551 nanometer. When the curing process is increasing, like the temperature is increasing, so that the wavelength, it is increasing. After the gel point, the density is increased, so the resin undergoes some pressure. So because undergoes some strain, so it is decreasing again, and it becomes a constant parameter. So by analyzing these results, we can able to monitor the curing process of the composite material. All these results are during the manufacturing of the blade. Here you can see the red one is the Fresnel reflection sensor output, and the black one is the FPG. As I mentioned in the previous slide, there are two sensors, FPG sensor as well as the Fresnel reflection sensor. Here, the completion process of the curing can be identified from both the sensor. On top of that, we also use the thermocouple as a measurement reference sensor. Here you can see the temperature outside the resin. That is this one. and temperature inside the resin. So here you can see the need for monitoring the temperature inside the sensor, inside the material is very important, because the ambient temperature, it will not increase very much. However, the internal composite material temperature, it increases drastically during the curing process. So there is a demand for sensor which can measure in situ temperature monitoring. So these are our results to show that fiber optic sensor can able to monitor the temperature and also strain inside the composite material. So this is the application of a fiber optic sensor in cryogenic temperature monitoring. What is cryogenic? Usually the temperature sensing, we always discuss about the room temperature, like or high temperature, like 500 degrees Celsius, 200 degrees Celsius. But there is another part, like which is called cryogenic. Here we always talk about the negative temperature, extremely low temperature. Here you can see the low temperature. These are the cryogenic liquids, liquid nitrogen. They have a temperature of around minus 200 degrees Celsius. So we need sensor which can measure negative temperatures, very low temperatures. I tell like, what is the need for measuring this negative temperature? What all the use of this type of low temperatures? So these are some materials which are producing the very low temperature environments. Liquid nitrogen, liquid fluorine, liquid oxygen, they have several applications. So one of the applications is aerospace application. Here you can see the cryogenic rocket engine. They use the fuel as a liquid nitrogen. Here I mentioned, right, like this is an oxidizer fuel tank. Usually the rocket engine, they use liquid fuel, the cryogenic fuel, which is extremely low temperature fuel. Here you can see the combination of liquid oxygen and liquid hydrogen offers high energy efficiency. So these are some applications which we never expect to know that they work on very low temperatures. We always think about like very high temperatures, but the fuel, what they use is for the negative temperature. And the medical applications. Here you can see in medicine, cryogenic cooling is used for diagnostic techniques such as MRI, and also they use cryosurgery, liquid nitrogen to kill the unhealthy tissue by freezing it. And also cryogenic plays an important role in transplanting the organs. And also here you can see the one of the application where we use the cryogenic liquid nitrogen. Here you can see the cooling of MRI electromagnet is very important, so that the magnification and the imaging quality is very good. It can be achieved only by maintaining the low temperature on the electromagnet. So these are some applications of cryogenic. And next is superconductivity. This is also one of the application of cryogenics. Superconductivity is a phenomenon of exactly zero electrical resistance. So when you send so this is one of the example where we use superconductivity. It's a zero electrical resistance and discharge of electromagnetic field occurring in certain materials when cooled below critical temperature. So this is one of the application. Usually why we use the cryogenic superconductivity is we need to have exceptional performance. The performance of a certain material can be achieved only at a very low temperature. So this is the one of the application. And these are some of the together applications like superconducting magnets, linear motor car, imaging system, transmission line, and magnetic energy storage. These are some applications. Here, need for temperature monitoring. Here you can see like what all the existing traditional temperature sensor like metallic resistance sensor, non-metallic resistance thermocouple. These are some traditional temperature sensor available for monitoring the cryogenic temperature sensing. So here you can see like silicon, like 60 Kelvin, and more below that 1 Kelvin, like these are some drawbacks, like whether it can be used in the radiation or whether it can be performed in presence of magnetic field. So these are some applications. So in this slide, you can see why traditional temperature sensor cannot be applied on this type of advanced field, because the requirement is like it should be low mass, small dimension, and insensitive to magnetic field. So this type of environment experience a very high magnetic field. In those cases, like normal sensors cannot be applied. And also in one traditional like temperature sensor, it can measure only one point. It is a single point sensor. However, in fiber optic sensor, it can measure several sensor at a single line, and also stability. It has a good stability, radiation resistance. This type of sensor, it cannot resist the radiations, and also distributed sensing is not possible. So none of the currently available sensor, it cannot satisfy the requirement of this advanced field. So the solution is fiber optic sensor. In this sensor, like I will present two schemes. The first scheme is using the Fpga grating for monitoring the temperature in composite material, and in scheme 2, I will present a low-cost fiber optic sensor for cryogenic temperature monitoring. Okay. So FPG, as I mentioned earlier, it is used for monitoring the temperature. In the room temperature, it can monitor well. It is linear. The reflected wavelength, it changes according to the temperature. But the sensitivity of this FPG is not very good. So in order to increase the FPG sensitivity, we use the additional coating. So FPG plus coating, it gives for multiple parameter sensing. Here you can see FPG alone, it can measure temperature, but with the coating, it can able to measure magnetic field, humidity, cryogenic temperature sensing, chemical and biological analytes. Here, our area of interest is cryogenic temperature sensing. So we are going to use a coating material on the FPG. The coating material is, it should have a high coefficient of thermal expansion, high Young modulus, sufficient addition to the bare FPG. For the long time use, if the addition is not good, there can be the performance issues may rise. So this is the main requirement. We use two polymer coating, epoxy and acrylate on the FPG, and it is cured, and this is the curing method, isothermally cured. It is deep coated, and it is normal FPG. After the polymer coating, it become a polymer coated FPG. Here you can see the FPG. This is normal FPG, and on top of that, we do the polymer coating. So this FPG can monitor the temperature. Here you can see, as I told, like normal FPG. Here you can see the bare FPG. In the positive temperature, the FPG can work very well. However, in the negative temperature, minus 175 degree, the bare FPG is, the sensitivity is not good, and also the sensor performance is not good. So in order to overcome that, we coated the FPG with acrylate and also epoxy. Here you can see the sensor sensitivity is very good for the temperature. It can monitor, like here, almost 10 times more sensitive than the bare FPG, the epoxy coated. Acrylate shows a better performance. However, the epoxy coated, it shows a really good performance at the negative temperature. Here you can see the scale is like almost minus 200 degrees Celsius we are sensing. So we use the epoxy coated FPG sensor for our experiments. So here you can see FPG. We use two FPG. The FPG, it is sensitive to both temperature and also the strain. So this is normal FPG, and we use the polymer coating. As I told, like it is sensitive to both temperature and strain. Here we use a temperature capillary tube. to avoid the sensor effect by strain. So this part, it can measure both strain as well as temperature, but here, because of this capillary tube, it can measure only the temperature effect. Here there is no strain effect. So this is a sensor setup. So using this sensor setup, you can measure the temperature here and strain and temperature, and strain can be calculated by minusing this, like subtracting this value. So this is our sensor. We embed this sensor on composite material. Why composite material? Because as I told, like composite material, it is applied on all the advanced applications because of this good factors like lightweight, good performance. Here you can see the composite fuel tanks in space shuttle, and also LNG, liquid nitrogen gas companies. They use the LNG tanks with the composite material. So this is the composite materials application. But if you see, like this type of composite material, when they hold this very low temperature liquids, there is a possibility they can produce some micro cracks in the composite material. So their application cannot be satisfied. So if there is a crack, there will be a leakage in the tank. So we need to monitor the structural health monitoring of the composite material in this temperature. So we use the fiber optic sensor for monitoring the temperature and as well as the strain of the composite material. Here you can see the composite material, fiberglass, and the material we use, epoxy resin curing agent. So this is the material what we use and their performance, like ratio, how they made. So this is the composite material we made, and we fabricated our sensor inside this material. So this is the experimental result of the curing process. I'll skip this one. Here you can see. So as the light will go from here, this is the broadband light source. It is going inside this. As I told, this is FPG sensor. It is a band rejection sensor. So it will reject one wavelength of light, and the remaining wavelength will be sent to this sensor. So here it will reflect one light. So two sensors can be like similar setup. You can monitor almost 1,000 sensors in the same sensor line. So this is one of the advantage. So this sensor is embedded inside the composite material. Here you can see the this FPG can monitor the strain and temperature, and this is only temperature. This is a demodulation technique what we use. So this work is already published in one of the leading journal, like in the optics field, applied optics, from our research group. So here you can see initially this is room temperature, cryogenic temperature. Cryogenic temperature is -180 degree. And here from -180 degree to room temperature. Initially in the room temperature, both the PCFPG, this is only temperature, and this is strain plus temperature. Initially all the value is 0. So the difference is also 0. Here the wavelength difference between the blue one is the difference between this one, that is the strain. So here initially it is there, but when you apply the liquid nitrogen, there is a difference. This is the strain produced on the composite material because of the liquid nitrogen. So here you can measure the strain value applied to the composite material because of liquid nitrogen. And in the cooling process, the strain is, in the warming up process, here the strain is removed. So by using this sensor setup, you can monitor both strain as well as the temperature inside the composite material. So this is one of our application. So here you can see the internal profile. We use reference temperature sensor, thermocouple sensor, in order to validate our sensor is working perfectly or not. So we compare the results. Our sensor performance is similar with the traditional thermocouple reference sensor. So the temperature monitoring is successful. And also here, as I told earlier, the need for measuring the internal temperature, in situ temperature, rather than the surface temperature. Here we use two thermocouple. One is embedded inside the composite material, one is on the surface. Here you can see the internal temperature and the surface temperature almost 15-degree variation. So there is always a need to measure the internal temperature rather than the surface temperature. So this is one of our application. And also the important factor is the response time. Response time of a temperature of a sensor is very important. It should be very minimum. So it should react very quickly. So here, if you see our temperature sensor, it has a good response time of less than 4 seconds. In this type of field, like 4-second response time is really good achievement. So we received that. And also the strain characteristics. We also validate our sensor whether it can monitor the strain very well or not. So we use a sensor for the comparison. Our sensor, it shows equally good response for monitoring the strain. So our setup can monitor both negative temperature and also the strain inside the composite material. So it is a simultaneous strain and temperature monitoring of a composite material at a very low temperature. So this is our one work. The second scheme is Fennel reflection based sensor for real-time cryogenic temperature measurement. So this is a second type of sensor which we use for cryogenic temperature. Here, I will explain the principle of this sensor. As I told earlier, the light from core medium, this is the inside the fiber core, and this is a composite material, like polymer material or thermosensitive material, which can detect the temperature. So the light, when passes from one medium of refractive index to the another medium, a part of a light will be reflected. So when the temperature of this, when the refractive index of this material change, the amount of light reflecting, it keeps changing. So it depends on this coating material. So if this coating material is sensitive to the temperature, it will change accordingly the refractive index. So here you can see the criteria for effective Fresnel sensor is variation in the refractive index of coating material greater than the change in the refractive index of the fiber. So here also we use two optical polymers, that is epoxy and PMMA. This is the material. This is before coating the fiber end, and this is after coating. So this is our sensor head, which is used for monitoring the cryogenic temperature. So this is our temperature setup. This is a broadband of light. It is sent towards the sensor. This is liquid nitrogen, which is almost minus 180 degrees Celsius. Here we use the reference sensor for temperature sensor to validate our work. Here you can see the sensing head. And this is a photo detector. So the reflecting light will be received here. And this is a data acquisition system to receive the signal. So this is our sensor setup. Here you can see the optical intensity. This is the received intensity from the sensor in this is Kelvin. So this is minus 180 degrees Celsius. The intensity is almost 8 dB. So when the temperature is at room temperature, it is like 0 dB, almost 8 dB difference we get using our sensor. So by analyzing this result, like we can validate that our sensor can monitor the very low temperature. So here also the epoxy coated sensor head shows a good performance compared to the normal PMMA, polymethyl methacrylate. It is acrylate coating, so it is showing a good performance. So we use the epoxy coated sensor for our further experiments. So this is the experimental results. Initially, it is in room temperature and liquid nitrogen is applied and it is warming up to room temperature. Here you can see the room temperature, the Here the red one is design sensor, and the thermocouple is traditional sensor. And we also use the PCFPG, that is another optical sensor I explained earlier, right? We are validating the sensor performance. Initially, the room temperature, the sensor, it is constant. After, when you apply the liquid nitrogen, the Fresnel reflection sensor shows the intensity change, whereas the thermocouple shows the optically, it shows inverted because temperature is decreasing, right? So it is like here you can see almost now 80 Kelvin, that is almost minus 180 degrees Celsius, and the temperature is increasing. And here the Fresnel reflection sensor response, it is same but in an opposite way of representation, because the optical intensity, it is increasing when the temperature is decreasing, whereas the thermocouple reading, it will decrease as per the temperature. So here we validate that our sensor can monitor the very low temperature. Here the repeatability, here we try to check whether our sensor is, whether it can shows a similar performance for every time we do the testing. So here you can see liquid nitrogen, again from 90 Kelvin, like all room temperature. So from liquid nitrogen to room temperature, minus 180 to room, minus 180 to room for different cycle, and our sensor shows a similar performance. So the sensor, it is validated that sensor can monitor very low temperature. So even this work has been probably also published in one of the leading journal in IEEE. So here we see the response time of our sensor. Here our Fresnel sensor, it shows a good response time, like almost 13 seconds. But here the response time is delayed because the sample is very big. Like here we already input the sensor inside the composite block. So it takes some time to cool down the composite block. So that is why it's showing the 13 second. And also here you can see the stability of our sensor. We almost keep the sensor in the temperature for liquid nitrogen temperature for almost 102 hours, and room temperature, the sensor performance it's not changed, it is very stable. So that is why like we validate like this sensor can monitor the temperature very well, and is also stable, and it is also repeatability is good. So this is the work, like comparison of work. There are several works which related to the cryogenic temperature monitoring. Among that, most of the work is Bragg wavelength, FPG based temperature sensing. There is no other previous work reported using the reflectance. It is our work, like we presented the new way of monitoring the temperature. So these are some list of publications of our work, what I presented now. Like it is published in several high profile journals, and also we have presented this work in several public conference publications. So this is my end of my presentation. Thank you. If you have any question, please feel free to.
Yeah, so thank you, Dr. Umesh, for the insightful talk. There are a few questions on the chat window I would like to ask for, behalf of the panelists. So,
okay. Yeah.
So there's a question from Mrs. Shaikh. He says that how can we polarize the sensor, and what are the parameters we can calculate by using the polarization?
Okay. Just a moment.
Yeah.
I can see. I'm just checking the comment section. Like, just thank you for.
Yeah, so I can read that for you. Like, would you be? Yeah, I can read that for you. So the question says, how can we polarize the sensor, and what are the parameters can we calculate by using the polarization?
In my presentation, like I've just given the brief intro, like the polarization related question, like sensor. My work is the presented work is fully based on the wavelength.
Okay.
So in-depth polarization, I'm not worked on that field. So my work, like mostly I work on the wavelength related field.
Okay. So then there is a question in relation to the wavelength. So you mentioned that you have worked with the wavelength sources of 1300 and 1500 nanometer.
Yeah.
Are there any specific reason for it? Like, why have you used the two wavelengths?
Like most of our sensor, like the fiber Bragg grating sensor, what we used is for this wavelength range. So as I mentioned, like just you can see my screen, right?
Yeah, we can, yes.
Yeah, here you can see the fiber Bragg grating. Here the wavelength for this sensor, it is calculated on this range, like for infrared range, like almost 1550 nanometer. So depend on this sensor, we can able to change the wavelength. If you are working on like a 1000 nanometer wavelength light source, then you have to design your sensor according to that range. So in our case, we designed our sensor for this wavelength range, 1550 nanometer. So we use the similar source.
So any specific reason why you used 1550 nanometer wavelength? Why do you design your sensor for 1550 nanometer?
Like most of the commercial applications, they use the 1550 nanometer wavelength source. It is widely available in market. So it is like most of the industries, they prefer to work on this wavelength range.
Okay. So there's another question from Dr. Naresh. So are there any sensitivity analysis you made, in comparison with conventional electronic sensors?
Actually, like the most of our applications, it is, as I told, like it is on the radiation environment field. Here you can see. Here you can see like the traditional sensor below, like whether it can be used in the radiation field. These sensors cannot be applicable in this type of environment. So in our case, like a fiber optic sensor is capable of applying in this type of environment. It is specifically designed, like we work on only specific applications. For this type of applications, we are trying to make a sensor. So here the sensitivity is not a big factor. Like the application is very important. Like normal sensor, it cannot be applied. So that is why, like, we go for the fiber optic sensor. If you need to increase the sensitivity, we have to work in depth on increasing how we can apply, that is a future studies, like how we can improve the sensitivity by selecting different materials. So material characteristics is also an important topic to think of if you talk about sensitivity. Yeah.
Okay. So there's one more question. And so what are the application difficulties of transducer over sensor?
Sorry, can you please repeat?
What are the application difficulties of transducer over sensor?
Transducer over sensor?
Yes.
What are the difficulties?
Application difficulties.
Sorry, sorry.
And there was one person, Mr. Nazir Unisa. Would you like to ask the question, please? Like, you can type in the question. We won't be able to, unmute yourself. And meanwhile, my colleague Dr. Sadish would ask the question.
So, Dr. Sampath, I have a question. I mean, what are the limitations of this type of optical sensors? Is there any limitations? I mean,
limitation is cost-wise, it is very expensive. That is a major, and also the setup is it is almost very expensive compared to the normal sensor, because the one Fpga sensor it cost almost like $70. Whereas for the $70, you can get a 10 to 15 meter, like almost 30 meters of thermocouple cable, and you can do the temperature sensing. However, as I told, like this type of advanced application, the cost is not a big issue. They need a high performance, and implementation is on this field is very important. So this type of advantages gives more room for development of fiber optic sensor. You cannot use the fiber optic sensor for day-to-day life applications because there is no any extreme conditions, right? So yeah, that is the main yeah.
Okay, thank you.
Yeah.
So thank you, Dr. Sampath, for your insightful and really a wonderful talk. And thank you for accepting our invitation. So I hope that our participants are benefited from your talk. Thank you, Dr. Sampath.
Yeah, thank you so much for organizing this wonderful event and to share my research experience with young people. And thank you so much for this opportunity.
Yeah, thank you once again. Thank you.
Okay, thank you.
And tomorrow is last day.
For the participants, tomorrow again we'll have 2 sessions. First from 2 p.m. to 3:30 p.m. and then last one from 3:30 to 5 p.m. So please do join those sessions. And specifically, the first session is on index modulation for 6G communication, and the session from 3:30 is intelligent reflecting surface assisted wireless communication for 6G. So please do join those sessions. Thank you.